review of the first kind of portion of Calc 2. So we're going to kind of go back, go over some concepts from the beginning of the class. We'll have some examples, and then you let me know if you do any of the examples or not. Does that sound good? Okay. So first we're looking at the integration by parts, right? Where we just have, which is useful when we have two functions multiplied together under the integral, and that makes it, right? We can't integrate it any other way than by doing integration by parts. And then the formula is on the right-hand side, right? We call it ultraviolet, where we pick one piece of the original function to be u and one to be dv. And then we integrate and derive the variable, fill in the equation. And then the pieces that we integrate or derive, right, that kind of depends on if we can tell it'll work its way out of our integral by taking derivatives, or if we can tell it's kind of going to be a loop, like maybe an e to the x or a trig function, right? That's probably a good one to pick to integrate, right? So we're just trying to simplify it as we go along. That's kind of the basic concept, and then we have some example problems. Do you want to work through any example problems? Or or we could set some up and then move from there. Mm-hmm. Exactly, right. Picking this to be our u dv, and then what would you do for the second one? Mm-hmm. Exactly. Mm-hmm. Yeah, and then so you choose that, they would cancel, and then we go from there. So I take these two to be my dv, this ln x piece to be my u, and then can you kind of tell what this third one might be? Mm-hmm. Right. Yeah. So number three, right, like you were saying, right, is the type where we'd have to do it twice, right? And we'll get the same form back after that second time running through the integration by parts so that we can add both of those same original integrals together and move it over. So yeah, you've got the setup for each of them, and then for each of from there you would just integrate, right? And then you'd be able to solve. So yeah, solid. So yeah, mostly the setup and what we do from there. And then that's just the run through for the solution, but seems like you've got a good hold on the topic. This part, yeah, is just walking through all the steps, right? Just like how you're describing. So if you feel like you've got a good idea of it, then yeah, that's kind of the end of that first topic is that integration by parts.
Okay. Okay. I'm doing partial fraction decomposition. How do you feel about partial fraction decomposition? Yes. Yep. So we have a couple examples. Do you feel like you would like to go through any of the examples? Okay. So you would do this as ax minus 2a plus bx plus 3b, right? And then you solve for your so x raised to the 0 power. You only have one of those, and then you set that equal to 3b minus 2a, and then x to the 1 power. You also have one of those, which is equal to a plus b, right? And then you can solve for your a's and b's. So you're saying A over 2x minus 1 plus B over 2x minus 1 squared plus C over x minus 1, correct? Yeah, you just do the same thing. Awesome. You're comfortable with that. You obviously know what you're doing. Okay, sounds good. I have the examples with the solutions, but I won't run through them. Okay.
Okay. So next we're looking at trig integrals, right? Where we just each time we approach with one of these problems, it's kind of all about evaluating the best substitutions to make, right? To simplify the integral. And this page is just kind of a reference for several of those, right? So you can look back at this as we look at examples. So what would your approach for this one be, right? We have one of the telltale signs that we need to sub is, right, this odd power, right? Mm-hmm. Right. Make sure it would be 1 minus cosine squared, right? Yep. Mm-hmm. Yep. And then it just becomes a u sub. On exams, so yeah. This is about referring back and making some wise substitutions. So yeah, you do that, you get your du, plug in all our pieces, and then after doing the u substitution and then plugging cosine x back into our u answer, we would get this answer at the bottom. But yep, you've got this set up and a good approach. And then this is, right, the other kind of trig integrals, which is less about direct identity substitution and more about simplifying this expression in terms of a trig integral. Do you have a method that you prefer for this, or do you want to walk through? That's what I like to do too. Yeah, right. You look at this, you say, okay, that looks a lot like the hypotenuse of a triangle. That's exactly what I like to do too, right? Building your triangle. That's supposed to be your right triangle. Mm-hmm. Yeah, so well, you can pick either to be the leg, right? And then you kind of have to decide where you want your kind of your theta or your angle to be to make it simpler, right? So for this case, I would say I know I'm gonna want to substitute for this square root term and for this dx term. And I know if I want a simple dx term, I want something that's going to equal 3x. So, right, like the tangent of theta equals 3x. That'd be super useful for me. I can divide that 3 over. And in order for that to be true, right, opposite over adjacent, I'm going to put my theta here, right? Mm-hmm. Yeah, I've seen that method as well. Um, but so yeah. And then, because yeah, a triangle is also nice because you can just assemble all the pieces, but there's lots of different ways. Some people just like to memorize it. Some people like to use right sine squared plus cosine squared and stuff like that. So do you feel pretty good about where we would go from here with the triangle approach? Hmm. Yeah, which we can go back to our reference, right, for the derivative of tangent secant squared. So we have, yeah. Mm-hmm. Because yeah, the reason we want to solve for x is so we can find a direct substitution for d of x, and we can plug that piece in. So we have our piece for d of x, and then based off of where our theta is and our hypotenuse, we know that cosine of theta equals the square root of 1 plus 9x squared. By the way, we built things, right? Then you can just plug all our pieces in. From there, we have the cosine theta. I'll pull out the 1/3 sine squared theta d theta. And then this is really nice because sine squared is just 1 over cosine squared, right? So we end up just with 1 secant left under, or after you cancel those terms out. And then you can just integrate from there, right? Which is kind of, it's not a super common one. It's the ln tan theta plus secant theta. But from there, you can plug all our pieces back into, we know what our tangent is when we know that 1 over the cosine is our, wait, 1 second. Yeah, let me fix that over there. Missed that part up there with the cosine, but to keep the hypotenuse on the bottom. But yep, from there we can just substitute back in for our trigonometries to get our final answer back in terms of x, right? Yeah. So yeah, lots of different methods, but yeah, triangle is good to kind of just get to assemble and work logic our way through things if we get stuck anywhere, right? Feel pretty good? Okay, awesome.
You forgot improper integrals? Yeah, they're not terrible, just you don't think about them too frequently. So improper integrals are any integral that is going to like infinity, or that is going from negative infinity to a point, or negative infinity to positive infinity. And then if the limit of the integral exists, then it converges. If it does not exist, then it's an improper integral and it diverges. Or if it goes to like infinity, then it also diverges. Go ahead. Yes, I'm just gonna close this door because it's a little bit loud. Okay, there we go. Yeah, so you are correct. So essentially, what we do is say the limit as we can call it b approaches infinity of the integral from 0 to b of actually I think we should call this yeah, we can do b. That's fine. Of 1 over x dx. Right? And then you find that limit. But as you can see, like this graph looks like it converges to it's just going to continue to go down towards 0, right? But because of this, that isn't actually true. It doesn't converge. So because this is the limit as b approaches infinity of the natural log of x evaluated from 0 to b. And then the limit as b approaches infinity of natural log of b. This graph goes to infinity.
That diverges, and if you were to put ln of x in the bottom, it would still convert. So technically square it, it diverges, but another way around.
Yeah.
Yeah.
But you definitely want to do it like this one. Yeah. Okay. So you're comfortable with that? Any more questions on this? Okay, sounds good. I have a lot of area to write in case I needed more. Okay, the next thing I'm gonna go over is polar coordinates, which is typically the last thing they do in class. Okay, sweet. So so your polar coordinates are where you're given an x and y point and you're trying to convert to r and theta. And yeah, I how do you feel about these? Okay. Yeah. Okay, we will run through some examples. We do have some equation. These are our equations equations for this section. So r is equal to, obviously it's using Pythagoras theorem, square root of x squared plus y squared. Yes. Yes. Yeah, for sure. And then your x is equal to r cosine of theta, which you can see from here. So if we wanted our x, sorry, I'll change the color maybe. I don't know how to change the color. Right here. Okay. Oh, I don't want that color. Oh, now it's gone. Okay, I guess I'm using yellow. Oh, that's actually fine. So this is our x. And then you know that theta, or that it's opposite over hypotenuse, right? So and it's cosine theta equals opposite or adjacent, sorry, equals x over r. So x is equal to r cosine theta. And you can do the same thing with the y and sine. Yeah. All right, I have a couple of examples. So we want to convert from rectangular to polar coordinates. So we want to find our r comma theta for this problem. So we are going, I'm actually going to use this. So we're going -3 in the x and up 4. So it'll be something out here. So this is -3 and this is up 4. That's a little high. This is 4, right? So we know that r is equal to x squared plus y squared, square rooted. So r is equal to the square root of -3 squared plus 4 squared. R is equal to the square root of 25, which is equal to 5. Right? And then we want to find our theta. So there's a couple ways you can find theta. You can use the theta is equal to arc tangent. Wow. Arc tangent of, I believe it's y over x, yes. Or you can use any of the x is equal to r cosine theta, or y is equal to r sine theta. Which one? Okay, I actually usually prefer to use this one or this one too. So, if we then want to solve for theta, we have theta is equal to arc cosine of x over r, right? So theta is equal to arc cosine of -3 over 5. And then you'll get theta is equal to 2.21 radians. I do want to point out that if you do use this arctangent, you will have to add, you'll get some number. So it'll be like 0 point something. You have to add pi to it to get it into the correct quadrant and to get that answer. Yes, you have to do it based off the quadrant it's in. So for this one, we know it's not in the first quadrant, so we would have to. Yes. All right, so are we good there? Any questions? Okay, awesome. Then I have this one converting from polar to rectangular coordinates. So we have r is equal to 2 and theta is equal to pi fourths. So we know that x is equal to r cosine theta and y is equal to r sine theta, right? So if we plug that in, we have 2 cosine of pi over 4, which is, do you know the cosine of pi over 4? Yes. So then you have 2 root 2 over 2, which is just equal to root 2. This one, 2 sine pi over 4 equals to, same thing, 2 root 2 over 2 equals to root 2. So then you would have your root 2, comma, root 2 equals to x, comma, y. Awesome. And then this one is a little bit tricky. I'm actually going to pull out my notes because I don't want to get lost and then lose what I'm doing. So do you have any ideas on how you would solve this one? Where you'd start? So you do have the right thought. However, it's r squared is equal to those things, right? So we would need to have r squared on this left-hand side. So to do this, we'd need to multiply by r through the whole thing. So then we'd have r squared equals to 6r cosine theta minus 8r sine theta. Now you can recognize that these, so we have x is equal to r cosine theta and y is equal to r sine theta. These here, this is your x and this is your y. And then you can plug in your x squared plus y squared on this left-hand side too. So then you'd have x squared plus y squared equals to 6x minus 8y. You can move everything over to the other side and you have x squared minus 6x plus y squared plus 8y equals to 0. Now, for these, we want to write this in the term of x plus or minus a value, so a squared, because then it's in the correct form, right? How do you think you would do this? Yes, so you want to complete the square. So to complete the square, so this should be x, it should be x squared plus b plus 2bx plus b squared, right? So if we know that the middle term has to be 2bx, it has to equal 6, so 6 equals to 2bx. We can then just solve for, we can get rid of that. 6 has to be equal to 2b, we can just solve for our b, so b is equal to 3. So then this would be, I'm gonna erase this so because I kind of wrote it really big. So then this here would be x squared minus 6x plus 9, right? What do we have to do on the right-hand side if we do it on the left-hand side? So if we add 9, we have to add 9 on both sides. Oh, you would do minus 9 here? Okay, yeah, that's fine. We can do it that way. And then the y, you would do the same thing. You would get y squared plus 8y plus 16 minus 16 equals 0. You can move both of these over to the other side. And then you have x minus 3 squared plus y plus 4 squared equals to 25, right? So what does this number tell you? Yes, so r is equal to 5. Yes. Mm-hmm. It's a tricky, it's just a tricky trick that you have to do. It's kind of interesting. But yes, you would have a circle, radius 5, centered at 3, comma -4. Which is just written here. And also this is the circle. I don't know why the circle showed up before everything else, but so it does pass through the origin. So yeah. All right. Is that it for today?
That's it, yeah.
Okay. Do you have any questions on any of that stuff? Oh, awesome. Fair enough. Good for you. Awesome. All right. Well, we do have, let me get to the end of the slides because we do have oh, that is not what I wanted to do.